Welcome my dear learners for this course on Design of Machine Elements 2. In module 3 we have discussed and designed spur gears and helical gears. Moving on to our module 4, in this module we will be designing bevel gears and worm gears. Let us move on to discuss the design procedure to be employed to completely design the bevel gears in this lecture. Before moving to discuss the procedure to design the bevel gear, let us discuss some basic topics regarding the bevel gear. The bevel gears are used where the power transmission should be taken place between the shafts whose axes will intersect. That is, considering two shafts containing the bevel gears, we will be using the bevel gears in which the axes of these two shafts are intersecting. From this diagram we can see that we have two bevel gears and two shafts. The axes of these two shafts are intersecting. Next, coming for the different types of bevel gears which we are going to design in this module. First one is right bevel gear. In case of right bevel gear, the angle between the axis of these two shafts, which is termed as shaft angle denoted by sigma, will be equal to 90 degrees, and the angle made by this line is termed as half pitch cone angle. Half pitch cone angle. That is, if I extend this edge such that it will intersect the point where these two axes are intersecting, I will get the two half pitch cone angles made by gear number 1 and gear number 2. So therefore, I can clearly state from the diagram the half pitch cone angle of gear 1 plus the half pitch cone angle of gear 2 will give us the shaft angle sigma. So therefore, sigma is equal to half pitch cone angle of gear 1 plus half pitch cone angle of gear 2. Next, moving on to the second type of bevel gear which we will be discussing is acute angle bevel gear. In case of acute angle bevel gear, the shaft angle will be less than 90 degree. Third type of bevel gear, that is obtuse angle bevel gear. In case of obtuse angle bevel gear, the shaft angle will be greater than 90 degree. That is, the shaft angle is greater than 90 degree. The shaft angle is nothing but the sum of half pitch cone angle of gear number 1 plus gear number 2. With this brief introduction to bevel gears, let us discuss the procedure which we are going to employ to design the bevel gear completely. Before moving on to the steps to to design the bevel gear, as I already said in our module 3, one should have the prerequisite to approach the problem. The prerequisites for design of gears are details of materials of gear and pinion, number of teeth on gear and pinion, and finally what form of module equation to be handled, which means that whether we are designing the problem in which the pitch circle diameter is known to us, or we are designing the problem in which pitch circle diameter is not known to us. So coming for the prerequisites, the first prerequisite is in what form the module equation to be handled for the given problem. That is, if pitch circle diameter is known to us, then solve the module equation in the form m into y. The module equation is given by equation 12.37 of page number 218 of our design data handbook, which is written by K. Mahadevan and Balaveera Reddy. We are referring 4th edition. Or if pitch circle diameter not given or known to us, then solve the same module equation, that is equation 12.37 present in page number 218 in the form m cube cv. Once you find the value of my in the problems of case wherein which PCD is known to us, or if you find the value of m cube cv in the problems in which pitch circle diameter is not known to us, we can find the module by trial and error method, which we have already employed in designing of spur gear and helical gears. The same trial and error procedure is employed to find the module. Once you find out the value of my or m cube cv. Next, moving on to the second prerequisite required to solve the problem on design of bevel gear is that the material details. Coming for the second prerequisite, if material details of both pinion and gear are not given, then for complete design, that is recommending the BHN, assume from table 12.7 page number 234 the material for pinion as alloy steel case hardened. Once you adopt alloy steel case hardened material for pinion, then as usual you equate sigma d1 y1 is equal to sigma d2 y2 and find sigma d2, which is nothing but allowable static stress of gear. Once you find the allowable static stress of gear, compare the value obtained with the values of allowable static stress present in the table 12.7 available in page number 234 and adopt the closest value for the value what we have got and also the material corresponding to that value of allowable static stress as the material for gear, where the values of y1 and y2 are nothing but Levy's form factor, which are given by equation number 12.5 C to 12.5 E. Or if you are designing the problem only for the first half, that is for the stage 1 of the problem, wherein which we will be determining the module and various forces acting on the bevel gear. For such problems, choose both pinion and gear are made up of cast steel 0.2% C heat treated material such that the allowable static stress of pinion will be equal to the allowable static stress of gear, which is taken from table 12.7 page number 234 of design data handbook. For complete design of bevel gear, in which you will be recommending the BHN, that is the surface hardness required for the gear pair, you should choose the pinion material as alloy steel case hardened, because if you observe table 12.7, the core hardness is highest for alloy steel case hardened material. For bevel gears, the hardness of the bevel gears should be very high compared to the spur gear and helical gears. Once you adopt alloy steel case hardened material for pinion, next as usual you employ the formula sigma d1 y1 is equal to sigma d2 y2 and find the value of sigma d2. Once you find the value of sigma d2, that is allowable static stress of gear, compare that value with the allowable statistics values present in the table 12.7 page number 234 and adopt the closest value of sigma d2 and also the corresponding material for gear. Or if you are solving the problem only to demonstrate the stage 1, that is to find the module and various forces acting on the bevel gear, then choose both gear and pinion are made up of same material, that is cast steel 0.2% carbon heat treated material, and design is for pinion, as we know that if both gear and pinion are made up of same material, always pinion will be the weaker member. Now moving on for the third prerequisite, that is number of teeth. If the number of teeth on pinion as well as gear is not given in the problem or not known to us, then for problems with PCD known to us, assume number of teeth on pinion as 20 only to find the weaker member. Thereafter replace Z by using the model equation, that is M is equal to D by Z, so therefore Z will become D by M. Coming for the second variety of problem, for problems in which PCD is not known to us, if the pitch circle diameter is not given or the center distance is not mentioned in the question, then for such problems in which the number of teeth is also not given, then refer table 12.4b page number 230 and adopt Z1. For M cube CV type of problems in which PCD is not known to us, refer table 12.4b. Based on the tooth form, you adopt the number of teeth on pinion to avoid the interference. Whereas for MY type of problems in which PCD is known to us or center distance is given, then assume the number of teeth as 20 only to find which is the weaker member. Thereafter you replace Z by D by M, where D is pitch circle diameter and M is module. With these prerequisite, we can design the bevel gears. Let us discuss the steps to design the bevel gears. Once we know in what form we should solve the model equation and the material details and also the number of teeth, we can solve the design of bevel gears. Moving on for the steps to solve the bevel gears. Step number 1 is to find the pitch angle of both pinion and gear. For acute angle bevel gears, that is the bevel gears in which the shaft angle is less than 90 degree, use equation 12.29a and 12.29b, which are present in page number 215, and find the pitch angle of pinion and pitch angle of gear. Else for right angle bevel gears, that is in the problem, if the shaft angle is given as 90 degree, and also this is the standard case which we will consider if the shaft angle is not mentioned in the question, then you should use equation 12.31a, 12.31b of page number 217. Or else if the problem is on obtuse angle bevel gear, that is if the shaft angle is given as greater than 90 degrees in the question, then you should use equation 12.32a and 12.32b, which are present in the same page number 217, to find the pitch angle of pinion and pitch angle of gear. Once you know the pitch angle of pinion and pitch angle of gear, step 2 is to find the formative number of teeth or equivalent number of teeth, which are equivalent to spur gear. Why we are determining the equivalent or formative number of teeth which are equivalent to spur gear is to find the Levy's form factor, because the Levy's form factor equation is not separately available for bevel gears. In order to use the Levy's form factor equations of spur gear, first we should determine the equivalent number of teeth. Use equation 12.35d present in page number 218, which is given by Z equivalent is equal to Z by cos delta, where delta is nothing but the pitch angle. Substituting the value of delta 1, I will get Z equivalent 1. Substituting the value of delta 2, I will get Z equivalent 2 with the corresponding values of Z1 and Z2. Once you find the equivalent or formative number of teeth on pinion and gear, you can find the Levy's form factor, which are available for spur gear by replacing Z by Z equivalent. That is step number 3 to find Levy's form factor. Use equation 12.5c to 12.5e based on the tooth form by replacing Z by Z equivalent. For example, if I consider 20 degree full depth, we should use equation 12.5d as y is equal to 0.154 minus 0.912 by Z equivalent. Once you find the Lewis form factor, you can determine the weaker member. Step 4 is to find the weaker member. As usual, you formulate the table, that is particular sigma d y product of sigma d into y, that is Lewis form factor, and finally remarks. Under particulars, you have pinion and gear. Enter the corresponding values. The lower value of sigma d and y will be the weaker member. Once you find the weaker member, the next step is to find the module. Step 5 is to find the module. In order to find the module, use equation 12.37 presenting page number 218 of our design data handbook, where Ft is calculated by using equation 12.8, which is nothing but 2mt by d, where mt is given by 9.55 into 10 to the power of 6 into p by n into cs, where cs is the service factor which is selected from table 12.8. So, referring to table 12.8, one can take the value of CS as 1.5 if not given. This value of service factor is taken as 1.5 by referring to table 12.8 by assuming the gears are working for 8 to 10 hours per day and subjected to medium shocks. Next, the P should be in kilowatts and N should be in RPM, where N will be N1 or N2 depending on the weaker member which we will detect. And in the same equation 12.37, we should know the value of velocity factor CV, phase width B and length L. Next, the value of CV is given by equation 12.38A or equation 12.38B presenting page number 219. If not specified, always assume the teeth are generated teeths and use CV is equal to 6.1 by 6.1 plus V, which is equation 12.38B. Next, moving for B, it's nothing but phase width B must be less than or equal to L by 3 from equation 12.36B of page number 218. Take B is equal to L by 3, where L is given by equation 12.33 of page number 217, which is given by L is equal to 1 by 2 square root of d1 square plus d2 square. And coming for the value of y, we already know that y is given by pi times the small y, where small y is Lewis form factor. For problems in which PCD is known to us, we should solve the problem for m into y. For problems in which the pitch circle diameter is not known to us, we should solve this module equation in the form m cube cv. In order to get the equation in the form m cube cv, express the unknown parameters with the help of module. That is, if I want to use diameter, then replace diameter by m into z, where m is module and z is number of teeth. Likewise, express all the unknowns with the help of module. Thereby, you can end up the module equation in the form of m cube cv for problems in which pitch circle diameter is not known to us. If pitch circle diameter is known to us, then we should form this equation in the form of m times small y and find the module by using trial and error method, which we have employed in designing spur gear and helical gear. Once you find the module, check the design for stress point of view. That is step number 6, checking for stress. In order to check the adopted module for induced stress, the procedure remains same. First you should find the sigma d into cv allowable. Then using equation 12.37 of page number 218, find sigma d into cv induced. For safe design, sigma d cv allowable should be greater than sigma d cv induced. And also you should check for allowable bending stress, which is given by sigma is equal to k2 square mt kc kd root of I square minus 1 whole divided by module into I capital Y k2 square minus 0.5 whole square L square cos alpha should be less than sigma d, which is given by equation 12.42 page number 219. So this equation should be satisfied. The value of sigma d is already known to us. If you are designing for gear, it is sigma d2. If you are designing for pinion, it is sigma d1. The value what you will get should be less than the value of sigma d, which we already know. Whereas this k2 is given by L by B, which is nothing but always 3. This is because of the reason B is L by 3, so therefore L and L will get cancelled. K2 will always be equal to 3. Coming for Kc and Kd, for Kc refer table 12.1 page number 235 of the data handbook, assuming cantilever pinion. Whereas for the value of Kd, refer table 12.11 page number 236, assuming medium accuracy of teeth and BHN greater than 350. Assuming BHN greater than 350 and medium accuracy of teeth, adopt the value of KD based on the velocity and based on the ratio of face width to pitch circle diameter, adopt the value of Kc by assuming cantilever pinion, referring to table 12.10 page number 235. So once you verify for the stress, the next step is to find the tooth proportions. that is moving on to step 7, that is proportions of bevel teeth. Calculate all the parameters of table 12.23a, page number 242 of our design data handbook, and also solve equation 12.30a and 12.30b of page number 215, and then calculate or solve equation 12.34b and 12.34c, presenting page number 217. And finally, you also calculate or solve equation 12.35a to 12.35c, presenting page number 218. So this completes our step 7, wherein which we will be calculating proportions of bevel teeth. Moving for step 8, that is to find bearing loads. Equation 12.45a to equation 12.45f of page number 219. So solve all these equations to find the various bearing loads acting on the straight bevel gear. And moving for step 9, that is to find dynamic load, use equation 12.40 of page number 219 of our design data handbook. The procedure to find the dynamic load remains same as the procedure what we have used to find the dynamic load on spur gear. And finally, moving on to our step 10, to find the hardness A when the core hardness of the materials are not specified in the question. If the core hardness is not specified in the question when giving the material for pinion and for gear, then use the general procedure what we are employing to find the hardness, that is using condition Fw greater than or equal to Fd. Already we have calculated the value of Fd in step 9. Now we know the value of Fw, which is given by d1 b q equivalent k by cos delta. This is equation number 12.4, page number 219. This is cos delta 1. So using this equation in the place of Fw, calculate value of k greater than or equal to. Now using the value of k from table 12.16, page number 239, recommend the BHM. This is the usual procedure which we have employed in the design of spur gear as well as in the design of helical gear. If the core hardness is specified in the question itself, then the case B is when the core hardness is given. If the core hardness is specified in the question, then we should verify whether the core hardness itself is enough to withstand the given working condition. If it fails, then we should find out the surface hardness required to withstand the given working condition. Now, to validate the core hardness, use equation 12.15D and find endurance stress. Then, using equation 12.15B, find the value of K, which are present in page number 208. Now, using that value of K, you recalculate the value of wear load. So now, using equation 12.41 of page number 219, calculate the wear load. Now, verify whether Fw is greater than or equal to Fd. If this condition is satisfied, then whatever the core hardness given in the question itself is the hardness for the pinion and gear material. If this condition fails, then you move back and find the value of K. Then you move back in the same manner and find the value of BHN, that is the limiting value of BHN, which must be required to withstand the given working condition. That is, if this condition is using wear load should be greater than or equal to Fd, that is, Fd is already calculated in step number 9. We know the formula for Fw. Find the value of K greater than or equal to. Once you find the value of K greater than or equal to, substitute this limiting value of K in this equation, find the limiting value of endurance stress. Now, substituting this limiting value of endurance stress in equation 12.15D, find the limiting value of BHN. Now, finally, from table 12.16 of page number 239, recommend the BHN. This completes the complete procedure to design the bevel gears. That's all from this lecture. Thank you.